Okay, good afternoon, advisors and committee members. Today will be the final presentation for our senior project application of low-cost vibration measurement devices for civil engineering structures. The contents for today, there will be three topics. First is about pedestrian bridge vibration. Second, the result and discussion. And the third will be the conclusion.
This experiment aims to identify any potential problems. The main problem with bridge is that it experiences notable vibration during pedestrian and large vehicle transport, as reported by the Bangkok Metropolitan Administration. This issue can potentially affect the stability and safety of the bridge. In order to gather data and analyze the problems, the time interval provided on May 12, which correspond to approximately 1 hour. The structural frequency is determined using the formulas as we show on the slide, and compared with low-cost device, the results show a close match between the calculated frequency and the device reading, indicating the device accuracy. Specifically, the frequency on the x-axis is found to be 5.24 Hz, while on the y-axis is 1.74 Hz. Performing the Fourier transformations on the graph show the natural frequencies of the bridge. The frequency in x-axis is 5.17 Hz, while the y-axis is 1.56 Hz. Notably, significant vibration is observed in the y-axis direction, closely matching to the typical walking pace of humans that average close to 2 pacing per second or 2 Hz. This suggests that the vibrations in the y-axis direction is mainly caused by the rhythmic walking of people. On the other hand, the y-axis display minimal vibrations as indicated by the graph amplitude.
This slide shows the result after we use Fourier transformation between the result from low-cost device and reference sensor. We can see from the graph that the dominant frequency in X and Y axis of 14-story building from low-cost device in normal situation is equal to 1 Hz. This value is clearly the same as the result 1 Hz from the reference sensor. And the natural frequency of 18-story building from low-cost device is equal to 0.915 Hz in both X and Y axis, which is close to 0.927 Hz in X axis and 0.878 Hz in Y axis from the reference sensor. This is the result of 60-story building, with the frequency results are the same between low-cost device and reference sensor, with frequency equal to 0.3 Hz in X axis and 0.1 Hz in Y axis. Our result indicates that the natural frequency from the low-cost device is as accurate as the result obtained from the reference sensor. So the low-cost device has enough capacity that can be used to determine the natural frequency of buildings. This is a sequence of natural frequency of building with different number of floors. We can observe that the natural frequency from low-cost device of a 7-story building is approximately 1.8 Hz and decreases gradually with 1 Hz in 14-floor building, 0.9 Hz in 18-story building, 0.4 Hz in X-axis, and 0.34 Hz in Y-axis in 31-story building until it reaches 0.33 Hz in X-axis and 0.1 Hz in Y-axis in 60-story building, which aligns with the theory that taller structures tend to have lower natural frequency due to their greater mass and stiffness. This slide shows the frequency graph of vibration from traffic inside axis between small vehicle and large vehicle passing through the device. We can see that the frequency graph obtained from a smaller car is flat. But when a large car passing through the low-cost device, it stimulates vibration, which can clearly show the dominant frequency inside axis to be equal to 3.4 Hz. Therefore, this low-cost device is effective in detecting the frequency of vibration generated by large vehicle movement during smooth traffic flow. This is the result of frequency and amplitude of frequency of the static axis at each distance of low-cost device from the traffic on the road. From the graph, we can see that the amplitude of dominant frequency is 63, 20, and 13, which decrease with increasing distance from the load. At the same time, the device still has the ability to measure the dominant frequency generated by traffic with a greater distance from the device as well. From 4.1 Hz with 0 m from the load, 4.2 Hz with 16 m from the load, and 3.4 Hz with 34.7 m from the load. The result provides strong evidence that the obtained data align with the theory of the weakening of propagated vibration due to distance. This finding further enhances the reliability of the device used for the measurement.
For the approach of noise reduction is to minimize random sensor noises by using multiple devices installed in proximity simultaneously. This approach can effectively smoothen the vibration curve, as you can see at the bottom here. This is the one before averaging, and this one is the after. As we zoomed in here, we can see that all these fuzziness get smoothened out after averaging, enhancing more reliability. Also, this visualize the amount of number of devices being employed at the same time. This having one device, this having two devices and three devices respectively. As you can see that the uncertainty of these amplitudes get lowered down very effectively. And for the constraints of the device, first is the limitation of vibration amplitude. The device possesses detection limit for vibration amplitudes below 0.2 millig due to noises, which resulting in unclear values. Also, the displayed vibration graph show a low correlation between the. Similarly, the second one is the noises, as I have explained earlier. This also poses problem for the measurement of vibration below 0.2, and this limitation posed by MEM's accelerator producing the noises, and this impact is it impacts the accuracy of the results. And the third is Fourier transform. The raw obtained vibration data or the plot of magnitude to time do not reflect significant interpretation of data. So Fourier transform is required to visualize and identify dominant frequency or another significant data for further analysis. Overall performance of the device, the ADXL355Z sensor detects vibration in different scenarios, including normal and external vibrations, as well as those attenuated with distance. It measures vibration along the X and Y axes, as shown by observed vibration curves. And the device shows comparable accuracy to reference sensor in displaying high intensity vibrations, making it a reliable and cost-effective option for precise measurement and vibration analysis application. And the third is the instrument proves its long-term usability by effectively measuring indoor ambient vibrations. Also, it maintains stable performance by requires continuous power and placement in a low traffic area for accurate measurement.
And there are 4 problems. The first one is installations of the device, supplies of electrical power, position stabilities of the device, and inaccessibility to the reference sensors. For the first problem, it's installations of the device, the need for internet connectivity to synchronize the device times and date with the current setting. Without proper synchronizations, the recorded data may not correspond to the actual experiment time. The solutions involve connecting the device to the Wi-Fi network or internet cable during the installation to synchronize the data and verify the current date and times. The second problem is the requirement for a constant power supply, which limits of the usability of the device in certain situations where access to the electrical outlet is limited. To overcome this limited the device can utilize a battery as an alternative power source. The third problem pertains to the stability of the device during experiment. To mitigate vibrations, it is important to securely affix the device to the surface using heavy objects or adhesive tape. This ensures that the device remains stationary and produces precise experimental results. Lastly, the inaccessibility of the reference sensor, which is often expensive but limited in the availability, pose a challenge in this experiment. However, by understanding the effectiveness and efficiency of the low-cost sensor, which can still analyze the available data effectively, overall, the solutions aim to enhance all of these problems.
For any future work related to this development, um, we recommend the development of applications such as interactive interface or real-time viewing. Also, we recommend streamlining installation so that installation is quicker and simpler, especially without using external power sources such as battery or electrical outlet. And the third is wireless network capability so that it can be connected to cloud and be viewed wherever and whenever. So in conclusions, device sufficiently capable of detecting vibrations in different scenarios, including external stimulation. The Fourier transform is applied to measure and display frequencies, aiding in estimating the natural frequency of buildings, provides highly considerable accurate vibration and frequency values. The device is durable and stable for collecting long-term vibration data, making it practical for various applications. Devices were successfully installed in vast locations such as buildings, roads, and suspension bridges, providing its versatility in engineering fields. The obtained results are somewhat capable of structural assessments and decision-making at some level. However, the device has limitation as it cannot measure values below 0.2 millig due to the noises posed by MEM's accelerator. Thank you so much for your time.
Yes, please the committee for question or comment.
I'll start first. One of the conclusion is you cannot measure anything less than 2 millig, right? Is that correct?
Yes.
Yes.
Is it conclusive?
Sorry?
Is it conclusive? Because at the moment, I mean, you how would I mean, at the moment you kind of claim that okay, your device or your device or your sensor is capable up to, you know, basically this is the resolutions of 0.2 or 2 milli. Is it 0.2 or 2?
0.2.
Yeah, it's 0.2 millig. Yeah, so I just wonder whether is there to make that conclusive, would you need some kind of statistical analysis to just really show that the you know the noise, this is the real noise. You know, anything below this is a noise, because it might not be. So for me, making that conclusion is quite strong. It doesn't mean that you can't conclude it, but I think it, in terms of your analysis, in noise analysis, is not enough. So that's my conclusion. So what I would probably suggest is I would probably won't make it conclusive. I would say, okay, you know, if anything below this, then probably need to be careful on applying this, but we don't know that for sure, because that needs to be tested in a lab first, experiment, or second needs to do some more noise analysis, because you really need to prove that okay, your level, your sensor is to, unless it's in the spec of unless it's in the spec of your accelerometer, then yeah, that I accept that, but at the moment it might not be. So that's my first comment. Do you have any explanation on that, or you think okay, maybe we just take that conclusion out?
Yeah, I think it makes sense.
So that's my first comment, and the other comment.
Before you move to the second, I am not clear about your comment, but from our observation, we cannot get anything below 0.2 milli-G. So that the conclusion from our observation. So what do you want to inspect further? How can we do that? Noise analysis.
The conclusion at the moment. Yeah. So from the observation, the conclusion is you should not apply anything. So the resolution is 0.2 milli-G. Is that so? So what I mean is because when a lot of data is coming from high frequency place, and then so if you have, let's say if you have if you can control the environment, and then you actually have, say you prove that this is really real noise and it cannot detect it, that's because my belief is it could be that it can detect below that or not. So I'm not so sure whether it needs more experiment or whether it needs some more statistical analysis, which I don't know how yet, but I need to look at some literature review. But I kind of just think that it might be that. So the conclusion is from the observation, from data, from real data, from like places, but it's not from control environment. So my conclusion is, yes, from observation, this is what we observe. So yes, I accept that you should not use it below this, but it's not conclusive for me because it can be better. So if it's better, then it's even better. But now it's like, okay, now this is what we get up to, which is fine. This is our limitation, but it might not be. So that's my comment. Yeah. Unless, as I mentioned, unless there's the spec of the sensor really say, okay, you cannot do it more than this anyway, because this is the spec. But if the spec say, okay, you can actually detect less than this, then yeah, maybe. So maybe control environment, because at the moment it looks like the conclusion observation come from real data, which is good, but it's not control. There's a lot of other factors. There's a lot of noise. Yeah, so I can't think of the other one yet. But อาจารย์ไม่ได้ก่อนได้นะครับ
Ajahn Monte, isn't it the 0.2 mg, isn't it the specification of the sensors?
Actually, in the specification is not tell about the level of noise, but in our observation, we found that if the amplitude is lower than 0.2 milli-G, it cannot observe from our sensor.
And this information is not in the specification of the sensor. There's nothing talking about this number?
Not talking about this number.
Okay.
It need to connect with the DAQ system also, so that we will know after we combine everything. So the specification we cannot get from the specification.
And is it important? I mean, 0.2 mg, is it important? Student,
yeah.
Do you think it's important?
I think it's important for environment where there is a very low vibration. It could be seismic activities which are sometimes not felt by human sensation, but it could be felt by the reference sensor, but because of our limitation of the developed device, yeah, I think that could be the one. And secondly, I believe some buildings also post natural frequency below that magnitude. So yeah, it could pose some limitations.
Okay. Well, okay. But I don't think so. I think it's not that serious. You have to think about the level of vibration that, for example, you have in your field measurement. You look at the level and then you compare that with this 0.2 mg. M is what? 10 minus 3, right? Yeah. And it's very small. And then you look at your data, the real data that you collect from vibration of the building, vibration from traffic. And this number 0.2 mg may be not that important. I'm not sure. But it has, I don't think it has to talk about frequency of the building. That one is not that is not relevant. Okay. My point is that let me see a graph when maybe the second or the third one that you're showing the vibration of buildings. Yeah, that one. Go back. Yeah, this one, the green one. What happened to the green one? It seems to going up. Yeah, that one. Did you hear me?
Yes.
What happened to the green one? Why is going up? What happened?
Replace the low cost device to measure the long term, and it maybe have some period that it may increase a little bit, but it will decrease to the normal as the past that it be.
And why is going up?
Maybe maybe it stimulates from the แรงภายนอกนะคะจาก
The wind?
External force.
And the first time that you saw this, you didn't feel anything about that? Why it's going up? Maybe it's going up forever, or you say that it will come down. But how can we know that it's going to go up or not? Maybe you have to explain that why. Maybe if you say that there's a kind of windy situation or whatever, but I don't know. But if you present the graph like this, you have to see that, well, why it's going up. Then you have to try to explain what happened. And maybe it's something about the term that you say, stability of the device. I don't know, because it seems to divert from. I'm not sure about that, right? So this one is quite, for me, it's quite clear that you should explain or talk at least something about it. And the second one is the conclusion. I think, well, in terms of frequencies domain. When you do the Fourier transform, represent the signals in frequency domain, and then you're trying to find the peak, the location of the peak, the frequency of the peak. That one, they are pretty good, right? Right, you can identify the frequency very good, but it's not surprise, I think, because it's easier to find the frequency, but the important one is the magnitude of the frequencies. Are they good? The magnitude of the peak, are they good? Comparing with the reference one. The thing is that we're talking in two domains, time and frequencies. In time domain, I don't see the comparison between the magnitude. Like, let's say the peak magnitude of the time domain. Are they good? Comparing with the reference one. In general, the peak in time domain, the peak from your device, your low-cost device, is going to be higher or lower than the reference one? Do you have an answer for that?
Second. Oh. Sorry.
You understand my question, right?
Yes.
Yeah.
So we want to show like the picture.
Okay.
I think you don't have in this slide, this presentation, you don't have the comparison of the magnitude, but we have it before.
We
I
just
think we
have 3 buildings. It's 14 and 18 and 60. The magnitude. It's found that it's nearest, like the low cost in this picture is in x-axis is 0.915 and the reference is 0.927. It's quite
well, I know that one is okay. But my question is, what about the height of the peak?
In y-axis, low cost device is more higher. Like in y-axis is the amplitude. In this low cost device in y-axis is 0.915 and the reference is 0.878. It's the amplitude.
No, you misunderstand about the y-axis, x-axis. They are to the plane xy. But what I'm talking here is the height of the peak.
The height of the peak.
Yeah, that 195, that is a vibration in x, vibration in y, the frequency is 195, but from the Fourier transform, the graph of the Fourier transform, the height of the peak, are they close together between the low cost and the reference one? Y is 0.068, right? Can you zoom it?
Before looking closely for the comparison, let me ask the student whether these two set of graph, whether they are measured at the same time or not. If they are different times, we cannot make any comparison. Do you remember that you got from the same time?
In the different time, but in the same time, just have only one experiment, which is 14 buildings. But in another two experiment at different time because
Okay, so this one simultaneous, right? Right? You measure simultaneous.
Sorry.
This is a
ได้ยินไหมคะ
ได้ยินครับ
so
ไม่ได้ยินแล้วครับ
ได้ละค่ะ so we put in the same time between the low cost device and different sensors just one experiment which is 14-story building and
So
for
this one, right? If
yes
this is
just only
one,
this one yes
yeah, can you
because,
zoom? Can you zoom in the graph, please?
can you see this as you see over here just wait a second it's
Sorry, my computer shut down unexpectedly.
เดี๋ยวก่อน
Ifอาจารย์นเรศ do you want to compare Fourier transform or do you want to compare the amplitude
graph.
from time domain?
Both of them.
Time domain. For time
Both
domain,
of them. Time domain.
Student, you can show the time domain comparison. I find it in your report. 3.15, figure 3.15. This is time domain comparison. This is exact time. Can you show?
3.15.
3.1 wait a second teacher
Page 37.
37 ใน report 37
Can you show it on the screen? You may ask Ajahn Krishna question also from this graph. You may answer Ajahn Krishna question also here. That can be, you can show about the noise level also from this graph. Can you show it on screen?
37
Okay. Sorry.
Oh no, another graph. 3.15. Yes, one. This one. 3.15 below. Yeah, this one. No.
3.15 figure 3.15
Yes, this one. Yeah, you may explain about this result.
This shows how much the noises interfere the overall result. As you can see on the red, that is from our
Yes.
low-pass sensor, and the blue one is from our reference sensor. As you can see at the beginning and at the end, which is before the induce of vibration, which it can represent the detection in low vibration environment. You can really see the contrast between these two values picked up by two devices. And you can see that the offset from the blue and from the red are the noises produced by the local device itself, which is not true and are caused by the MEMS accelerator.
No, but my point is that if you go to the next, please go to the next figure, next page. This is a zoom of. This is excitation, vibration due to the pushing of the building, right?
Yes.
Yes, and if we look at I'm talking about the difference in the amplitude. And if you think that is this from the noise, and then at the end you're saying that you can like cancel the noise by some levels, then I think you should show that it actually is like, because my question is about the height of the wave, the difference in the height, because when we talk about the accuracy, there's a accuracies in time domain and accuracy in frequency domain. But what you have here is just like you saying that they are not equal, they are not the same, there are some different, but I don't see the numbers, I don't see the values, like how many percents or whatever. If you think about the highest one, the highest vibration from the blue and from the red, you have some number for that. Like, for example, if I use your device to detect a vibration, if I am interested in, I want to find the maximum acceleration of the vibration. If I use this device, is it gonna be less than, equal, or in general higher than how many percent? Can you give some, can you talk about that? Let's say the real one, the true one is 0.1 G. And then I use this device to detect that maximum. Maybe I'm gonna get 0.08 or maybe 0.12. I think it is the information that should be addressed. Like, it's just a straightforward if we want to compare the accuracy.
Yeah, Atandare point is very important. But anyway, let me help them. Actually, this part is already done by Ajahn Amontep. He already compare with the check table for actually this graph, this figure 3.16 may not be a good example for comparison, because the sensor location are not exactly the same, and the fixing of the sensor is not good. Also, we just try to put it in the building. But Dr. Amontep already make a comparison on a checking table. He attached with the firm table and move them together. But that part is not student work, so they do not include in their report. But anyway, I understand that point, and student may need to take the part of comparison from Ajahn Amontep to put in your, I mean, in the literature review or something that the previous work has already done about the comparison of the sensor, and the result can be discussed only for reference, but not your work. Yeah, thank you.
Okay.
Ajahn Amontep, what about the accuracy? You can comment about it.
I have many cases that I make a comparison between reference sensor and low-cost sensor, and the results show that the accuracy both of amplitude of time history and amplitude of frequency domain is quite similar between two sensors in many cases. And I will give you some my report.
Okay, similar means like, or you are showing your report now.
I can show you my presentation.
So do we have time? We have another group, right?
The next group start at 2 o'clock from 2.
Okay.
Can you see my
Yeah,
slide?
yeah.
Yes, I make a comparison between reference sensor and low-cost sensor in the first time on checking table and on building. And this is the result from checking table with checking amplitude, checking frequency 0.2 Hertz and amplitude is 15 millimeters. And this figure shows the zoom of graph between low cost in red line and reference sensor in black line. The amplitude is quite similar. And the amplitude of frequency domain is also similar. But the red line is from low cost sensor. There are some noise in the low frequency, but the amplitude is very similar. You can see this figure. And also the auto peak of frequency domain, the low cost sensor can detect all of frequencies.
What about the time domain? You have some numbers, like the maximum vibration that.
I'm not mentioned in this slide, but the approximately is about 0.015 or 0.02 G something. And I have many cases. The next is frequency on check table is 0.5. Amplitude is quite similar. And this is the result from ambient vibration on the building. You can see the red from low cost sensor. So you can see limitation of this sensor. If the vibration amplitude is lower than limitation of sensor, it cannot detect, but the reference sensor can detect.
And
but
then
the amplitude.
so that 0.2 mg is it important?
If you want to make a measurement of ambient vibration, so 0.2 is important. But if you want to make a measurement of the earthquake or wind or storm, I think 0.2 is not much important. But because the amplitude of that force is higher than 0.2 milli-G.
Why the last one? Well, that 0.2 mg that we're talking about, when we look at the upper right figure, how can you know that it cannot detect the 0.2? Because it seems like on the upper right figure, we have vibration both from the reference and the low cost one. And it seems that the amplitude of the red one is what? The red one is
low cost.
The low cost one is in fact higher, right?
0.2, 0.3 milli-G allow this amplitude.
No, I mean the amplitude in time domain of the low cost sensor is in fact higher. The true one.
Yes, maybe.
So it's higher, and then why are you talking about the limitation of 0.2?
In many cases, I think this is the result from our first experiment. So we after that we fix program. We use software to help us to reduce the noise. So recently we found that if the amplitude of vibration is lower than 0.2, allow this amplitude, we cannot get the signal from the low cost.
Okay. Well, I'm sorry about that. I'm just curious. Thank you, Ajahn Amonteep.
Yeah.
I'm just confused that why the amplitude from the low cost one is higher.
I think because the noise is combined into the real vibration. So noise is added to the real signal. So it show higher. But when we measure higher amplitude of vibration, the low cost sensor work well. But this is the problem of the very small amplitude that cause some problem.
Yeah, we're talking about noise, or we're talking about the error. The error. Because I think we have to think about what is the noise, what is it, and the error is the noise. What is the error?
You can say anything, any terms. They are. We don't want them.
Yeah, because if it is a noise, it's a random. It should be random, right? If the error maybe there's some. Okay.
But
it's random, and Amonteep or yes.
That's what I meant. I mean, like when you said about 0.2 milli-G, I mean, it could be noise. It could be if it's a real noise, then you can definitely model it. You can use Monte Carlo or something to model noise using. Because so and then you can actually subtract it to your original signal, and then when you do Monte Carlo, it should give you some kind of average noise level. But that is beyond your scope. It's not for your project to do.
Okay, I have no further questions. Very good job for students.
Yeah, very good. Got one more questions on the sensor. You said you put you averaging 3 signal from 3 sensors to damp the noise, right? So you smoothing by using. So is that the limitation? Does that mean I need to use 3 sensors to make sure that my result is accurate?
By applying more devices, we found that the noises can be eliminated at some point, but as you might see in the graph, it reduces, but it does not effectively eliminate them at all. So this approach just works at some number of devices being deployed. So we cannot indefinitely put up as much devices as we want, or else it would be cost the same as a reference sensor. But for some work that the magnitude of the noises are insignificant, then yes, we can definitely use the device for the work.
Yeah. Okay. Anyway, so yeah, so there's some noise tolerance that we need to just look at whether it's noise or errors. Yeah, something to, because they don't give you the spec of a sensor, I mean, if it does, then you know the resolution of it immediately. But yeah, so I have no more question, Kap. But well done, very good job.
ไม่มีก็ขอบคุณอาจารย์ทุกคนนะครับเราไม่ได้สอบกลุ่มนี้ไม่ได้สอบห้องนี้ต่อใช่ไหมครับ ห้องอื่นแล้วเนาะ
ของผมไม่ได้อยู่ไม่มี
อาจารย์วิโรจน์ห้องไหนวิเดี๋ยวต้องไปหาก่อนได้ครับ
อา
ขอบ
จาร
คุณ
ย์
ครั
กฤษดานี่กี่โมงตอนนี้เนี่ย
เที่ยงคืนครับ
อาจารย์วิโรจน์อยู่ไหนนะอยู่ไหนฮะ
ผมอยู่แคลิฟอร์เนียครับ
ที่ไปสแตนฟอร์ดใช่ไหมฮะ
อันนั้น September อันนี้อีกคอนเฟรนซ์หนึ่งครับ
อ๋อเหรอโอเคจะไปเจอเตยองไหมครับจะไปเจอเตยองไหมเนี่ย
ไม่ได้เจอครับรอบนี้ไม่ได้นัดมาน่าจะเจอรอบหน้ารอบนี้
แต่นุ่นเขียนไปได้บอกเขาเตยองเขาว่าถ้าเกิดสนใจไปเขียนไปเลยบอกว่า
อ๋อ
ยังไงเขา extend
เดี๋ยว
ให้อยู่แล้ว
ทุนไม่น่าพอ
ไม่มีแล้ว
ครับอาจารย์
โอเคครับ
ใช่
ปีหน้า
ครับ
ปีหน้านะครับ ปีหน้านะครับ เป็นจูนปีหน้า
อ้าวเหรออ๋อโอเค
จูน
ได้
ปี
เดี๋ยวผมดู
2024ครับ
ครับได้เดี๋ยวผมดูอีกที
โอเคได้ครับ
ครับสวัส
ครั
ดี
บ
ค
ข
รั
อ
บบ
คุณครับนักศึกษา
ขอบคุณ
ขอสั้นๆเดี๋ยวคุยกันผมสั้นๆ 2-3 นาทีเดี๋ยวผมต้องไปสอบอีกกลุ่มหนึ่งนะครับแต่ว่า
โชคดี
สั้นๆ
ค
นะ
รับโชคดี
ขอบคุณมากครับ
ครับโชคดี
มีเปิดมาเหวอๆนิดนึงตกใจอยู่ๆจะมาพูดถึงเรื่อง pedestrian เลยเหรอ ผมก็ตกใจนึกว่าจะพูดแต่ pedestrian เนาะจริงๆแล้วน่าจะเล่าว่าเราทำอะไรมานะฮะไม่เป็นไรก็มันไม่ต้องแก้ตัวหรอกหมายถึงว่าผมคอมเมนต์ว่าเราควรจะเล่าตั้งแต่แรกว่ามันมีอะไรที่เราทำมาบ้างแม้กระทั่งไอ้ตัว human synchronization ตัวนั้นก็เล่าได้สั้นๆนะแล้วก็บอกว่าสิ่งที่เราจะมาเพิ่มคืออะไรเนาะแล้วค่อยขยายความมาต่อนี้นะครับที่ผมอยากจะให้ลองทำให้ผมดูนิดนึงก็คือว่าไอ้ตึก60 ชั้นเนี่ยทำไม y axis มันถึงผิดไปจากตัว reference sensor เยอะเหมือนกัน reference sensor ได้0.14หรือไงเนี่ยแล้ว y แล้วของเราได้เป็น0.18ผมว่าเราอาจจะต้องใช้สัญญาณยาวกว่านี้เนาะเราหยิบมาแค่สัญญาณเดียวหรือเปล่าสัญญาณที่เราอยากหยิบมาวิเคราะห์เนี่ยมันแค่อันเดียวหรือเปล่าเราอาจจะหยิบมายาวกว่านี้นะ60 ชั้นน่ะมันไม่น่าผิดไปเยอะอะ
เพราะเหมือนตอนเช็คตอนแรกมันเท่ากัน
มันน่าจะมีอะไรที่มันดีกว่านี้ใช้ยาวๆหน่อยใช้นานๆเลยนะแล้วลองดูซิว่ามัน improve ขึ้นไหม reference sensor น่าจะถูกอยู่แล้ว reference sensor ใช้10 นาทีก็ถูกแต่ของเราถ้าเกิดหยิบไอ้ตัวสัญญาณที่มันต่ำมากๆมามันอาจจะเพี้ยนไปนะครับ
อันนี้เหรอคะอาจารย์
ใช่ไหม0.18กับ0.146เนี่ยมันไกลกันมากเลยนะ0.335กับ0.41ก็ยังพอโอเคอยู่แต่ว่า0.18กับ0.46นี่สงสัยอยู่ลองหยิบช่วงเวลาอื่นมาดูหน่อยนะครับ
ได้ค่ะ
แล้วอันอื่นๆมีอะไรไหมเนี่ย ผมไม่แน่ใจว่าเรา
มี
จะ
เส
ต้
ริ
อง
ม
แก้
คือ
ครับ
ไอ้กราฟที่เราใส่ในรายงานนะครับ หน่วยแกน y มันผิดนะครับลองดูในรายงานตั้งแต่หน้ามีเยอะเลยครับลองดูนะครับไอ้อย่างหน้าที่77หรือหน้า78ของ PDF อะครับลอง77ก็ได้ครับหน้านี้ไหมที่เขียนบนหัวเพจ77ครับเนี่ยแกนลองซูมเข้าไปแกน y
เดี๋ยวผมต้องไปต่ออีกห้องหนึ่งแล้วนะ แต่ว่าเดี๋ยวเราคุยกันทางไลน์กันได้เนาะถ้าอาจารย์มาเทศมีอะไรก็คุยกับนักศึกษาไปก่อน แต่ว่าฝากกลับเรื่องอีกเรื่องหนึ่งก็คือที่เมื่อกี้นะเดี๋ยวเอาผลที่อาจารย์นมาเทศเคยตรวจสอบความถูกต้องไปแล้วมาช่วยอธิบายด้วยนะจะได้สมบูรณ์ไปแล้วยังไงเดี๋ยวมีผลยังไงเดี๋ยวคุยกันทางไลน์ทางอะไรนะครับเดี๋ยวผมต้องไปสอบเป็นกลุ่มหนึ่งเนาะครับแล้วดีละภาพรวมครับดีนะครับผมครับผมครับสวัสดีครับ
เดี๋ยวผมต่ออีกหน่อยนึงก็ได้นะครับก็ไอ้แกน y เนี่ยหน่วยมันเราแปลงหน่วยผิดป่ะนี่มัน200มิลลิจีไม่น่าจะถูกมันน่าจะเป็น 0.2 หรือเปล่าอันนี้มันน่าจะ
200คูณ10อ๋อแต่หน่วยในกราฟใช่ไหมคะ
แก
มัน
น y
200 คูณ 10 กำลัง
มันไม่เห็น
นี่มันคูณ10อ๋อไม่เห็นใช่ไหมโอเค
มันเหมือนเราครอปรูปมาหรือเปล่า แล้วก็มันเป็นอย่างเงี้ยเกือบตั้งแต่หน้านี้มั้งไล่ไปเรื่อยๆเลยครับ ก็จะเห็นตัวเลขเป็น400บ้าง500บ้างอะไล่ลองหน้า
เหมือนอย่างนี้นะครับ
มันน่าจะเป็นไอ้นั่นมันของแกน x ไง
ไม่แต่ว่าถ้า200 มิลลิจีมันก็มัน 0.2 G
0.2
เลยถูกไหม
จริงๆไอ้ตัวนี้มันต้องเป็นระดับ 0.2 มิลลิจีถูกไหม
อ๋อ
มันต้อง
โอเค
คูณ10 กำลังลบ
-3 ใช่
3คือถ้าเราแปลงหน่วยผิดก็แสดงว่าเราครอปหัว แต่ไม่น่าจะ ถ้าครอปไอ้ตัวแกนอื่นยังไงมันก็ต้องมีห้อยคูณ10 กำลังลบ 3ไว้ข้างบนทุกอันนะ
ค่ะ
อันนี้น่าจะลองไปเช็คใน MATLAB ดูครับว่ามันถูกไหม ก็เป็นอย่างนี้หมดเลย แล้วก็หน้า87ไม่รู้เราพิมพ์ตั้งใจพิมพ์อย่างนี้อยู่แล้วหรือเปล่า f เท่ากับ0 เฮิร์ตซ์หรือพิมพ์ตก
อันนี้เหรอครับ
ใช่ครับ มันต้องเป็น0 จุดอะไรปะมันเป็น0 เฮิร์ตซ์เลยเหรอ
ไม่ค่ะ
น่าจะราวเลขไป
ใช่ไหม มันน่าจะมีตัวเลขเนาะลองเช็คดูนะครับ แล้วก็หน้าแรกๆที่มันมีกราฟที่เราไปพอตใน Excel เองครับ ฟอร์แมตมันไม่ค่อยเหมือนกับเพื่อนเขา แล้วก็แกนคำอธิบายแกนก็ไม่มีด้วย อย่างหน้า44ครับ 3.3.3.5 กราฟพวกเนี้ยครับ แกน x ไม่ได้เขียนไว้ว่าเป็นแกนเวลา แล้วก็แกน y ไม่ได้เขียนว่าเป็น amplitude เป็นความเร่งหน่วยอะไรพวกเนี้ย ก็ให้เขียนแล้วก็ถ้าเป็นไปได้ทำให้มันเป็นกราฟฟอร์แมตเดียวกันทั้งเล่มน่าจะสวยกว่า เอาไป
แล้วสมมติว่า
ไหนก็ได้
ถ้าเราเขียนเพิ่มแบบข้างใต้รูปได้ไหมคะ แบบ x คืออันนี้ y คืออันนี้
ก็ได้นะ แต่เขาก็ต้องมาอ่านคำอธิบายนะแต่ในส่วนตัวผมนะ ถ้ามันอยู่ในกราฟทั้งหมดเลยมันก็จะดูกราฟทีเดียวก็เข้าใจเลย ก็แล้วก็
Excel
format
เข้าคอม
ปรับ format ให้มันคล้ายๆกันทั้งเล่มมันจะดูน่าดูสวยขึ้นเนาะ
ได้ค่ะ
ก็ไม่มีเลย แต่ที่จริงไอ้กราฟที่เปรียบเทียบกับตึก14 ชั้นนะที่จริงมันไม่ได้อยู่ชั้นเดียวกันนะจำที่บอกได้ไหมว่าไอ้
ที่
ที่
มัน
เป็น
วาง
ไอ้เซนเซอร์ที่อยู่ข้างบนมันไม่มีข้อมูล มันต้องเอาอีกชั้นหนึ่งมาเทียบแอมพลิจูดมันก็เลยไม่เป๊ะกัน 100% นะครับก็มีประมาณนี้ครับโดยรวมก็ดีแล้วครับเดี๋ยวผมจะส่งไปให้ในกลุ่มนะครับไอ้ตัวรายงานตัวรูปอะไรลองเอาไปแปะดูครับอธิบายเพิ่มโอเคครับก็ประมาณนี้
ไว้ในเขียนอ้างอิงไว้ใน literature review ใช่ไหมครับ
ก็ได้ครับได้ เพราะว่ามันก็เป็นรายงานความก้าวหน้าที่ผมส่งมาอะไรก็เอาไว้เป็นliterature ก็ได้ โอเคครับก็ประมาณนี้ครับ
ได้ค่ะขอบคุณมาก
โอเคครับสวัสดีครับ
ขอบคุณครับหายไวๆนะครับอาจารย์
ครับขอบคุณครับผม